Hello and welcome to Fun with Physics with Uncle Bob. This week we'll be looking at an old problem called the Brachistochrone problem. That problem is to optimize the curved path that an object slides down for minimum time from top to bottom. So we vary this path, try to get a minimum time while this object is acting under the influence of gravity. What I will be doing today is solving this problem while it is undergoing both friction and drag. So what I've done is written a program in Power Basic, and I've broken up a curved path, as you've seen drawn here, into many small points, I plus 1 with a distance d between them. So an object on this path here, say I here, is undergoing a gravitational force directly downward, mg, which can be broken up into two components. One component here, which is the driving force for this object going parallel to the path, that's this right here, mg sine alpha. And then a component normal to the path right here, mg cosine alpha, going straight into the path. This normal force will cause friction, a kinetic friction, and also will contribute to centripetal force friction because of the curved nature of this path. I'll discuss that in a moment. In addition, we've got drag, air drag. Well, you'll be using turbulent drag as this object slides down the path. So we've got one driving force, the parallel portion of this, of the gravitational force driving this down, three retarding forces. One, the kinetic friction as it slides down due to this component. The other is centripetal force acceleration, which causes additional friction due to this component. And the third I just mentioned will be the drag force from air resistance. So we'll go on and look at a centripetal force that I've just mentioned. That's calculated this way. It should be fairly obvious. Go from I to I plus 1. We've got to change d alpha here, and the acceleration is, of course, v squared over r, as shown here. You can feel free to stop this, pause it in your video at any time, and look further at it. I'm going to go on now to the main equation, combining all the things I just said. The force acting on this particle or object as it slides down this path, resultant is F, given here of these components. The mg sine theta, which I mentioned, is the driving force, and then we've got the three retarding forces, friction here, and then drag, explained here. So what we do later, or I've done, is come down and using these equations here, with a known d, we calculate the distance between each point. We plug in our acceleration here, come down here, and find t from this equation, solve this equation for t. This gives us our new velocity. So there you go. Let's look at the problem itself. This is the program I wrote in Power Basic to model this problem. It uses very small random perturbations in the initial straight line slope to search for a curve with a lower time. When found, the slope is plotted below the initial straight line slope. Then this process is repeated many times and achieves better and better curves. All curves remain plotted on the output, so you can see the successive approximation process at work. Due to the random search method used, there will be very small variations in optimum time shown in the output at the end of each run when the same input values are used. What I'll do is move this up feel free to pause your video if you want to copy this or look at it so you can see the whole program. Moving it up slowly. Pause. Moving up slowly. Next page. That's it. So let's take a look at some output on the screen. I'll do some example runs of the program here. What you're about to see on the output screen will be initially the straight line slope going from upper left to lower right as the object slides down. It goes fairly quickly. Immediately below that you'll see successive dark lines filling in, getting successive optimized solutions. Once that's stabilized, we've got a nice curve below that, the optimized solution. That will go off, immediately followed by a blue cycloid for comparison. And then finally the blue cycloid curve will be overlaid with my optimized solution so we can compare them. So here we go. Watch what happens. Straight line at the top, filling in better and better solutions. This bottom of the dark area is the optimized solution. It's stabilized. In a few seconds this will go off and we'll see a blue cycloid there, immediately overlaid by, there it is, the optimized solution. Notice that with no friction, no drag, these curves are identical, as expected. Times here, straight line, optimized, a good savings in time. Let's go on. And next example, we'll put in sliding friction only and run it. Be the same procedure, filling in. Not quite as deep in the belly down here. This is optimized just about now. It's stabilized. There's our cycloid overlaid by sliding friction example. Times should have gone up, and indeed they have here, as you can see. Next, I'll take out the sliding friction and put in air drag only and run it. There we go. Blue cycloid coming up, and then the optimized solution for air drag right here. Times shown here. Last example, we'll put in both friction, kinetic sliding friction, and air drag proportional to velocity squared. So this would be a lot of retarding forces on this. As you see, this stabilized pretty quickly, fairly close to the straight line as expected. Cycloid, optimized solution, and your times have gone up quite a bit. There you go. Have fun with the program, and we'll see you next time.